Swayam Prabha. Digital India. Educated India.
The next basic element is a capacitor. And it's given by the symbol. As usual, we define a voltage V and a current I consistent with passive sign convention. I think from basic physics classes, all of you would be familiar with the prototype structure of a capacitor, which consists of two parallel plates, okay, with some area and some distance between them, okay. And again, from basic physics, you would know that if you apply a certain voltage V between the plates, that causes a charge plus Q on the plate which is connected to the positive of this voltage V, and minus Q which is connected to the negative of this voltage V, okay. And the relationship between Q and V happens to be linear with a proportionality constant C, which is called the capacitance, okay. C is the capacitance measured in farads. So what it means is, if you have a 1 farad capacitance, you apply 1 volt across it, there will be 1 coulomb of charge on each of the plates. There will be plus 1 coulomb on the plate which is connected to the positive side of the voltage, and minus 1 coulomb on the other plate, okay. And this C itself is given by some permittivity times area divided by the distance, okay. Now, as before, we are not concerned with these details. We are not concerned with what charges there are. We are not concerned with fields inside the capacitor and so on. We only want a relationship between the terminal current and the terminal voltage, okay. That is the voltage between the terminals and the current through the terminals, okay. And also, this type of formula, this works for a case where you have two parallel plates separated by a uniform distance. Now, if the shapes are odd and the distance keeps changing, you have to evaluate this capacitance using electromagnetics, using some integrals and so on. So again, that's not our concern at all. The point is, if you have two conductors separated by some insulating medium, you will have this linear relationship between charge and voltage, okay, which we will now convert to relationship between current and voltage, okay, and we will use that. So as far as the circuits are concerned, the terminal relationship between the current and voltage is good enough, okay. Now, how do we do that? This current I flowing, which is the same as the current I flowing in this terminal, is given by the rate of change of charge. That's the definition of current, right? If this Q is increasing, that means that there is some current flowing that way. In fact, that current is what is causing the Q to increase. Now, from physics, you know that there are these fields, and when you have these time varying fields, you will have currents and so on. It's known as displacement current. Again, we won't worry about that. We'll have some voltage across this, and current can flow in response to this voltage, or voltage can be changing in response to the current, okay. Now, from this relationship, we have C times dV by dt. It's of course assumed that the capacitance itself is a constant, okay. This is a given for all the capacitors that we will be using. So we have this relationship I equals C times dV by dt, and This is the VI relationship of a capacitor. The current is related to the time derivative of the voltage across the capacitor. Now this comes from the linear relationship between charge and voltage, which we have converted to a relationship between current and voltage. Okay, so for the purpose of analyzing circuits, this is the relationship we will be using. Because the IV relationship of a capacitor consists of a time derivative, we cannot draw a graph of I versus V. Okay, so that's possible only if a particular value of V gives a particular value of I or vice versa. Okay, in this case it's not possible. Now what does this say? If V is increasing at the rate of, let's say, 1 volts per second, and C is, let's say, 1 microfarad, this means that I is C times dV by dt is 1 microfarad times 1 volt per second equals 1 microampere. So 1 microampere current will be flowing through the capacitor. Okay. It also implies another thing, that if the current is finite, that is, if the circuit is such that the current through the capacitor is restricted to a finite value, then the voltage across the capacitor cannot change abruptly. Okay. So if the currents are finite, the voltage across the capacitor has to be continuous. On the other hand, if you do find a discontinuity in the voltage across a capacitor, that means that the current had to be infinite at the instant of the discontinuity. Okay, because a voltage changing instantaneously means that the charge on the plates of the capacitor changing instantaneously. That means that the current, which is the rate of change of charge, is infinite, because there was a certain non-zero charge change in a zero time interval, so that means an infinite current. Okay. I is given by C dV by dt, and if you invert this, we get the voltage to be 1 over C integral I dt. Okay. Now if I carry out the integral from some t0 to t1, okay, what it says is V of t1 is 1 over C integral I dt plus V of t0. Okay, that is, the change in the voltage between t0 and t1 is the integral of the current, which is the charge accumulated between t0 and t1, divided by the capacitance C. Okay. So let's say the current follows some waveform like this, and this is t0 and this is t1. I have drawn it versus time, and if you plot the voltage, it has some value at t equals t0. This is the voltage, and it will increase in some way, and at t1 it will be V of t1, and this increase V of t1 minus V of t0 is given by the area under this curve, area under the current curve, divided by C. Okay. So this whole thing equals the area under the current curve divided by C. So that's what this is saying. Okay. Now, because of this integral relationship, there is some memory, right? The initial value of the capacitor's voltage appears here. So, a capacitor is said to be an element with memory. It remembers what happened before. Okay, the voltage at a particular instant is not related to the current at that instant, but the current at all the previous instants. Okay, so that's why a capacitor has memory. Okay, and this is also apparent from the terminology normally used to describe a capacitor, like it stores charge and so on. Okay, and this is in contrast to a resistor whose current depends only on the voltage at that instant, or whose voltage at a given instant depends only on the current at that instant. Okay, a resistor has no memory.